Welcome to a new lecture of conformal diagrams in general relativity. In previous lecture, we studied the conformal diagram of Minkowski spacetime, and today we are going to carry out with the study of the conformal diagrams of de Sitter spacetime and anti-de Sitter spacetime. Well, these three spacetimes belong to the simplest possible solution of the Einstein field equations. And I would like to start this lecture by explaining why those spacetimes are the simplest solutions, and in a sense, why I mean by the simplest solutions. To do that, I need to remind you of a concept of differential geometry, which is the notion of sectional curvature. What is the sectional curvature? Okay, suppose we have a pseudo-Riemannian manifold. It can be space-time. And let us take two vector fields. I'm going to use this notation. Okay, so this U and V are smooth vector fields defined on M. Then the sectional curvature is defined as follows. Where the brackets are an abbreviation for the scalar product with respect to the metric. Okay, right. So, well, the sectional curvature has a clear geometric interpretation, which I'm not going to discuss here. But what I'm going to discuss is the case in which the sectional curvature is constant, which means that this scalar quantity is independent on the chosen smooth vector fields, okay? Right. When that happens, we say that our spacetime is a spacetime of constant sectional curvature. And the thing is that it's possible to classify this kind of spacetimes. And this is what the following theorem shows. Riemann tensor of a pseudo-Riemannian manifold which is of constant sectional curvature has a very specific form. Okay, and this k0 is a constant which a simple computation shows that is the sectional curvature. Okay, right. So what is more, this structure of the Riemann tensor also implies that the metric can be written in a very specific form in certain coordinates. Okay. Where here eta mu nu is the flat metric, the flat pseudo-Riemannian metric in Euclidean coordinates. Well, maybe I should write this below. Okay, right. So, okay, I'm not going to give the proof of this result, which can be found in a number of textbooks. For example, in the very old classic book, Eisenhardt. I don't remember the year, but just is. The title is Riemannian Geometry. There, for example, you can find a proof of this result. But anyway, for us, the important point is that we can use this expression of the metric to classify the spacetimes which satisfy this property. And this is so because the classification comes according to the sign of the constant sectional curvature. Okay, so because we have explicitly here the sectional curvature in the expression of the metric, so we have three situations: the case in which k0 is positive, the case in which k0 is 0, and the case in which k0 is negative. Okay. Okay. And in fact, well, if we pick this expression of the Riemann tensor and we compute the Ricci scalar, okay, first we have to compute Ricci tensor. very simple computation. Well, I think I don't think I need to give the details. It's just I'm just going to give you the result. Okay, and from here we get that the scalar curvature is proportional to the sectional curvature. Okay, so we can classify the spaces according to the sign of the scalar curvature. Well, and so these three cases are the case in which scalar curvature is positive, and well, this will correspond to the Sitter solution. The case in which the scalar curvature is 0, which corresponds to, well, just look at the expression of the Riemann tensor. K0 0 means the Riemann tensor is 0, so this is the Minkowski solution, which we have already studied. And then we have the case in which scalar curvature is negative, and this is the anti-de Sitter solution. Okay. And why do I keep saying that these are solutions of the Einstein equations? Well, this has a very simple answer, because if you just remember Einstein equations with cosmological constant, and well, we assume that we are in vacuum, so energy momentum tensor is 0, then, well, it's easy to see that these equations are satisfied by these spaces, because, well, we have here the expression of Ricci tensor, and we have the expression of the scalar curvature, so we see that these equations are fulfilled for certain values of the cosmological constant lambda. It's just a matter of doing a simple replacement. Well, I think I will just write everything in terms of K0. Okay, so this is this means that if we just pick up well, sorry, this is with the plus. So we just pick up lambda equal to 3 times K0. Then we see that spaces with constant sectional curvature are a solution of the vacuum Einstein equations with cosmological constant. And again, we have now the classification which I have just written, but in terms of the cosmological constant. So I could just write this with the cosmological constant. Well, of course, in this case, this is just vacuum with 0 cosmological constant, and this is with the negative cosmological constant. Okay, so the reason why I said that these are the simplest solutions of the Einstein equations is because these three spaces are spaces of constant sectional curvature, and they fulfill the vacuum Einstein equation with cosmological constant, which in the case of Minkowski is the cosmological constant equal to 0. Okay? Right. So this was just the geometric motivation for the study of these three cases. We have already studied Minkowski in the previous lecture, and now in this lecture we are going to study de Sitter solution and anti-de Sitter solution. Okay. Right. So let us start with de Sitter solution. It's normally written small letters. Okay, well, previous theorem already gave us a form for the metric of the Sitter solution, but, well, there are a number of ways of getting this metric. Here we are going to present a way which is normally followed in textbooks, which is maybe more intuitive than the metric which one gets from the previous theorem. And the way in which one can, well, it's more intuitive because it enables us to visualize the Sitter spacetime. And the way of getting the metric is just, okay, we are going to see the Sitter solution as a subset of 5-dimensional flat Minkowski spacetime. Okay, so now let us just consider 5-dimensional flat Minkowski spacetime, and so let us define a subset of these L5 as follows. Okay, where here A is a constant. Okay, maybe just it's a real constant, and well, this can be, well, this is well, if you remember the equation of a hyperboloid in lower dimensions, you recognize here that this is just a hyperboloid, but in 5 dimensions. Okay. Remember the expression of the hyperboloid, just a standard 2-dimensional hyperboloid, right? And so this is the same, but now with more coordinates. So this is very simple to understand that we are looking at a hyperboloid here. Well, but for our purposes, we need a metric in 4 dimensions. So we need to find a parametrization of this hypersurface of L5, and then get the first fundamental form of this hypersurface, because this first fundamental form will give us the 4-dimensional metric which we need to perform our analysis. Okay, and well, it's just a matter of finding a convenient parametrization. I will write down the parametrization which we are going to use. So Okay. So this is the parameterization, and well, you may have immediately recognized that chi, theta, and phi are angles on the 3 sphere. This is because, well, the topology of this set, well, I mentioned a hyperboloid, but when you carry this out to higher dimensions, in this case of well, this hypersurface regarded as a set embedded in 5 dimensions, well, is a codimension 1 hypersurface, and its topology is S3 cross R. Okay. Which is the topology of the zeta spacetime. Okay. Yes, and well, it's just one has to find the differentials of these expressions and plug them in our original expression of flat 5-dimensional Minkowski, and this gives you the first fundamental form of this codimension 1 hypersurface. I'm not going to carry out the computation here. I'll just show you the result. Okay. And so this is the metric of the zeta spacetime. Well, in this expression, well, this is the metric of the round 3 sphere. And so, well, it's clear when we look at this expression why I'm saying that the topology of the zeta is R cross S3. Well, maybe this would get even clearer if we just look at a picture of the hyperboloid. Right? I have already prepared a picture for you. Okay, now it's a bit big. I have to rescale the picture to make it smaller. Okay, here it is. Right, so, well, I cannot draw in 4 dimensions, so I have to drop 2 dimensions out in order to draw the picture. And, well, these circles are hypersurface with T constant. So they will have the topology of S3, so they are the S3 part. And then we have this vertical, well, these lines with chi constant which represent the R part of the topology. Okay. Yeah, well, yeah, just I'm saying that this is a codimension 1 hypersurface embedded in 5 dimensions. So just let me draw the 5-dimensional axis. Okay. And so, well, this hypersurface, this hyperboloid, gives us a visualization of the zither spacetime. Okay, right. And now, once we have this visualization, we want to learn about the global causal structure of this solution, and so we will perform a similar procedure as the one we did for Minkowski spacetime, right? Remember what we did in the case of Minkowski spacetime. We found a conformal embedding of Minkowski spacetime into Einstein static universe. So next we are going to do something similar in the de Sitter spacetime. Okay? Okay, right. Well, and so, well, let me just let us just take the metric which we have obtained. Okay. Let us put the metric here. And let us find a conformal embedding. Well, the procedure is similar to what we did for the case of Minkowski, so I'm not going to explain all the details. We're going to do a number of coordinate transformations. On this initial metric, and in the end we will obtain an expression which will allow us to read off the conformal embedding. Okay, let us start. Well, there's something which I forgot to say, and is this is constant, and well, it's actually related to the cosmological constant. I don't think we need the explicit relation in this lecture, but just for the sake of completeness, let me just write that A is equal to over, okay, right. Okay, so let us just carry out the transformations. Well, this is the first this is the transformation which we need. Well, it's actually the inverse of this transformation, because we are just doing a transformation which involves only the coordinate t. Okay, so okay, the inverse is just a very simple computation. Is just okay. So, well, it's just a simple manipulation. I will not. Well, perhaps I should just give an intermediate step. Let me just think. Okay, well, just have to take the differential of this expression, put it here, and then do this replacement and do some computations, I just write an intermediate result. I encourage you to do the complete computation. Okay. And here, well, I am adopting the okay, well, let me just do it a bit better, just because. I'm just adopting the standard abbreviation of naming the round 3 sphere, the metric on the round 3 sphere by d omega 3 squared. So this is this. And well, it's just now playing a bit with the properties of the trigonometric functions to find the final result, which is remarkably simple. And again, we recognize here the Einstein static universe. Okay, so it means that if we follow the procedure, we follow the reasoning which we did with the Einstein, with the Minkowski spacetime, we can construct an embedding such that this corresponds to the pullback of the original metric corresponds to this part, and which is the Einstein static universe. Okay, so it means that right. So okay, so we have the explicit conformal embedding of de Sitter spacetime into the Einstein static universe. So we only need to find the conformal boundary, which is found just as we know by finding the zeros of the conformal factor, which we define as the chi function. Here is easier than in the case of Minkowski because we have only one coordinate involved, which is the t. Okay, so right? Okay, all very simple. Well, something, well, in fact, well, you see that there are an infinite set of zeros And well, situation is sort of similar to the situation which we had in Minkowski, where we had also an infinite. You remember, we had an infinite set of lines, of straight lines, which represented the zeros of the chi function, and but in the end we only needed to pick a subset of these zeros. Here something similar happens. So if we just draw picture, okay, maybe here perhaps I can just draw right. Well, okay. Again, I am using chi for the chi function, and I'm using chi for a coordinate for one of the coordinates on the round on the 3 sphere. I hope that there's no confusion. Well, see that there's chi tilde, so there shouldn't be any confusion. But just and yeah, so we have and well, an infinite number of lines. Well, and chi it's varies between 0 and pi. So we have to just consider a vertical line. Maybe I will just use a thinner pen to draw this line. Okay. So yeah, so that's what we have. And then, so we only need to care, since chi goes from, we remember this restriction, it means that we only need to care about this set, and also, well, we have to pick up one of the regions which are between the horizontal lines. So we just pick up the easiest one, which is going to be this. Sorry, let me just use again the thin pen. Okay, and so this sort of rectangle is going to represent the zither solution. But again, we need to think this is a two-dimensional representation, but we need to work in more than two dimensions. We need to work in 4 dimensions, but as always, it's not possible to draw here from 4 dimensions. I can only, at most, I can just draw a 2-dimensional representation of something which is 3-dimensional. So let us again take a picture of the Einstein static universe, which is a cylinder, as you know. Again, we'll have to do the usual rescaling. Okay, so here it is. And we have to take this square and put it into the cylinder. Okay. Right. So, and well, this is what has been already done here, right? So you see here, it's just that, well, you remember that T in the Einstein cylinder goes from goes along the axis of the cylinder. So it's and since we have that our region goes from T minus pi half to T equal to pi half. So we just have to cut the cylinder at T equal minus pi half and T equal to pi half. And this is what I have done here. This is the boundary, the conformal boundary, which well corresponds to these horizontal lines. Okay. And yeah, these circles corresponds to the S3 of the Einstein Einstein static universe, which also in this case correspond to the S3 of the de Sitter solution. Okay, so yeah, so you see here this part of the cylinder is the image of de Sitter under the conformal embedding. Sorry. Okay. Right. And again, you see here that the closure of the image is compact. So this is indeed a conformal compactification. And what else? Yeah, and well, I have drawn in red the conformal boundary, and in this case, well, it's just two sets, which is future now infinity and past now infinity. And well, just by looking at the picture, we easily realize that the topology of each of them is just S3. So in this case, we have conformal boundary appears to be simpler than in the case of Minkowski solution. Okay, but what are the consequences of such a conformal boundary? What does this conformal boundary tell us about the global structure of the Sitter solution? Well, let us discuss this now. Okay, well, and for doing that discussion, let us just take this rectangle and draw it a bit bigger. Okay. Well, basically what we need to do is just take this cylinder and unwrap it and put it in a two-dimensional representation. So you just imagine that we take this, we open it up, and we get a rectangle. Right. So let's just draw this rectangle. It's here. And okay, the vertical lines, have some vertical lines here, correspond to constant values of the chi coordinate. So we can say here that yeah, so well, and then, well, this has to remember. Okay. Right, and well, what is the first important thing here? Well, this is similar to the case of Minkowski. We remember what null lines look like in the Einstein cylinder, and so that enables us to draw here the null lines, which are again lines with a 45-degree slope. Well, again, it's better to use the thinner pen just to get a nicer picture. Well, this should go from, I'm just going to delete this part to make it nice, because this just to give the, this is, well, it's not easy to draw 45 degree slope, but I think you can more or less imagine that. Okay, sorry, this was, okay, now this is one, this is another one, this is another one, this is another one. Okay, and so the knowledge of the null rays enables us to draw causal curve, inextensible causal curves. For example, I'm just going to draw an inextensible causal curve. Since the curve is causal, its slope has to be between two null rays. Okay, give another one. And by doing that, we notice that all inextensible causal curves start and end on the conformal boundary. Okay, so you see that any inextensible causal curve has an endpoint on past null infinity and has an endpoint on future null infinity. By the way, here, and also another property, well, we are using the name null just because light rays are also null curves, so are also causal curves, and so the same applies to them. Well, it might look like, well, just remember that this line is identified with this line, and so if we have a curve which has an endpoint here, we have to just think that the curve continues on the other side. Okay, so this is pretty much what happens when you project the surface of the Earth on the plane. So we have this goes here, this continues on this side, and then these null rays, which you are seeing here, also have endpoints at the conformal boundary. So that's why we're using the name null. But the point is that now these are hypersurfaces on the Einstein cylinder, and now it turns out that they're space-like hypersurfaces. Okay. Well, maybe. Okay, right. So, yeah, that's what we have. Yeah. Yeah, and the fact that these are space-like bring some, well, is somehow the reason why we have this property that any curve has an endpoint in future and past now infinity, any causal curve. And well, there are also other consequences of this property. A property which we can see just by looking at the diagram is that for any causal inextensible curve, we have the following. Okay. And well, you remember from the previous lecture what the future and chronological past is. So it means that the future and chronological past of any causal inextensible curve is always a proper subset of the sitter. There are no causal curves such that the future or chronological past of it is the whole de Sitter. Okay, this is not true. Okay, so well, you can, for example, well, just I don't know, just pick this curve. Okay, then let me just draw its chronological past. Well, just have to remember the definition of chronological past and just look at the curves representing the null rays, and you realize that it is this shaded region represents its chronological past, and well, I can also draw its chronological future. Well, because you just have to think a bit about the definition of chronological past. So these are the set of points which can be reached from a point of the curve by means of a time-like path. Okay, and so you just look at this picture and see that not any point of de Sitter satisfies this property. Okay, and the same, something similar happens with the chronological past. So when this happens, we say that the particle gamma has a particle horizon, because, well, the definition is as follows. We have, well, in black. We have the following definitions. Okay, and so in this in de Sitter, this is always different from the empty set for any curve. This was not true in the case of Minkowski. Remember that there were curves such that this set was these sets were empty sets. Somehow we can, well, if you just look at the diagram again and just see the just look a bit at future null infinity and past null infinity, we see that they are horizontal lines. They are space-like hypersurfaces on the Einstein static universe, and the fact that they are space-like is responsible somehow for the existence of these particle horizons. Remember that in Minkowski, these two were null hypersurfaces, and the very fact that they were null hypersurfaces implied that for some curves these sets were empty. Here, since these are space-like, then for any curve these sets are non-empty. Okay, and also we see that just by looking at this diagram, that it's possible to find Cauchy hypersurfaces. Okay, so I'm just going to draw a hypersurface, call it sigma, and well, I think it's already evident just from this picture that any causal inextensible curve in the picture will always have to meet sigma at some point. There's no way for a causal inextensible curve to avoid meeting sigma. Again, you have to bear in mind that this line and this line are identified. Okay, so just by looking at the picture again, we can guess that de Sitter is globally hyperbolic. So, to summarize, we have found that these the diagrams which we obtain, the conformal diagrams which we obtain in Minkowski and de Sitter have of different shapes. In Minkowski, it was a triangle, sort of triangle. Here we have a kind of a square, and this has already brought some differences. For example, the existence of particle horizon for any costal inextensible curve, but still both Minkowski and de Sitter are globally hyperbolic because we have found a Cauchy hypersurface. Okay, so there are different properties, but they're also similar properties. Well, another thing is that well, in this case of de Sitter, we have been able to obtain the main information about the global causal structure by just studying a two-dimensional diagram. So in this case, when since the diagram is two-dimensional, we can well, I refer to the diagram as conformal diagram, but we can also use the name Penrose diagram. So I'll say that this is the Penrose diagram of de Sitter. Okay. Whenever we can just reduce the study to 2 dimensions, we speak about Penrose diagram. Okay. Right. Well, and now this is de Sitter. The next case is anti-de Sitter. Okay, well, we already mentioned that ADS is a space of negative curvature, negative constant sectional curvature, but as happens with de Sitter, there is an alternative representation of anti-de Sitter, which will help us to get a geometric picture of this space. And what is this geometric representation? Well, to show this representation, let us consider now again 5-dimensional flat spacetime. Okay, but now it's not going to be flat Minkowski, it's going to be something a bit different. Well, what notation should I maybe I don't know. Yeah, I think that probably the best is this notation. Okay, and what do I mean by this? Well, is flat spacetime with the following line element. Okay, so well, this is not Minkowski because we don't have Lorentzian signature. We have two coordinates playing the role of time. Okay, so in a sense, that's why I'm using this notation to indicate that the signature is not Lorentzian signature, is another signature. And well, it turns out that ADS anti-de Sitter in 4 dimensions can be regarded as a subset of this space, which is defined as follows. So again, this is going to be a condition on the set of points which are in this space, and the condition is the following one. Okay, so well, you see that this is a sort of hyperboloid, but now it's not quite, because we have two minuses, so we cannot say that this is hyperboloid. And well, the point is that if you have a set which satisfies this condition on R5, because well, which is just an element of R5, then it's not well, it can be seen that the topology of this set is just S1 cross R3. Well, this is independent on the metric. I mean, just well, forget about the metric just for a moment and just concentrate on this definition, just the set of points of R5 such that they satisfy this condition. Okay, well, this is enough to show that the topology of this set is given by this is S1 times R3. Well, when I mean, I'm not going to give a formal proof of this, but well, one can sort of guess that this is so, because well, you can just take the set of points such that x1 plus x2 square x2 square plus x3 square is some constant k. Okay, then this means that x0 square plus x4 square is what is minus a square minus a square minus plus k square, right? And well, the topology of this set, okay, for a given value of k, well, of course, one has to choose this in such a way that k square minus a square is positive. Okay, so well, and for a value of k, the topology of this set is just S1, because this is the equation of a circle in the plane x not x4, right? So this accounts for the S1 which we have here, and then if we vary this constant, what we get is a foliation of R3 by spheres, because well, this is for each value of k, this is just the equation of a sphere. So this accounts for the R3, right? And this doesn't require any it doesn't require that we have a metric in R5 at all. Okay, well, this is not a formal proof, but it's just an argument which makes it plausible that one has this topology for this set without appealing to the existence of a metric. But anyway, the important thing is that, well, we need the metric, and the thing is that if we find the first fundamental form of this hypersurface embedded in this space, we will get something which is, of course, it's a four-dimensional metric, and this will correspond to the metric of ADS4. And how are we going to do that? Well, it's same as we did before with the sitter. It's just we need to find a parameterization, and well, the parameterization which we are going to use is the following one. Okay, so well, you'll see that we are somehow adapting. We are finding adapted coordinates to the S2 we have, sorry, the S1 we have here, and the relation which has spherical symmetry. Okay, because well, so well, again, it's just a simple computation to find the first fundamental form. So we only need to differentiate each of these relations and replace them back here in the expression of the metric in dimension 5, right? Well, well, it's very easy if you're familiar with the elementary manipulations of differential geometry. Well, this is just going to give us the spherical line element in dimension 3. Okay, so one has that 1 plus dx2 plus dx3 is equal to dr plus r squared. Okay, and as for this couple, it's just computing the differentials, which is also, well, it's a very simple computation, and finding the squares. I'm not going to do the full computation. I'm just going to give the result, but I hope that you can carry out the computation yourselves. Okay, so that's what we have, and then so we only need to put the two pieces together and obtain the four-dimensional metric. Well, it's just adding these two terms, and well, after some elementary algebra, you get I don't think you'll have much of a trouble in getting this expression. Well, something has happened here, and is the following. And if we just look at this metric, well, we need to remember something important when here, and is that the metric, when we have a pseudo-Riemannian manifold, okay, well, the metric doesn't determine the topology of the manifold, okay? So it just only gives, well, actually, in general, the metric is just defined locally. But it may happen that one has metrics with, one has manifolds with with different topologies. So they are in fact different differentiable manifolds, but they have the same metric. Okay, well, it's very simple, just in 2 dimensions. With 2 dimensions, just think about a plane and a cylinder. Okay, so they are both flat. They have both the flat 2-dimensional metric, but their topologies are different. And something similar has happened here, because we started with something whose topology is S1 cross R3, and now we have found well, that the metric of this object is this thing, and it turns out that this metric also may exist in a space whose topology is R4. Okay, so in this case, well, well, you can also guess that by looking at the expression of the metric, because, well, this part has topology R, and this part has topology R3, because, well, this is just well, is flat. Well, if this term was absent, then this could be just flat Minkowski, flat Euclidean 3-dimensional space with this term in. Well, this is still defined for any value of any positive value of R. So this is not introducing any change in the topology. So the topology of this space is R3. So we can regard this this metric as a metric defined in a space of topology R4. So and so what has happened here? How we started from something which I said has topology R cross S3, and now we end up in something which has topology R4. Well, the reason why this is happening is because, well, this metric can be defined in our original set with this topology, but it can also be defined in another manifold whose topology is R4. Well, we can visualize that if we just, well, do a picture of this set. Okay, well, we can just, I prepared the picture for you, so I'm just going to put it in. Okay, just give me a second. Okay, so here we have the picture. Let me just rescale it first. Okay. Okay, so yeah, one has to think. One has to imagine that this is that we are in R5. I mean, that this is a picture in R5. Well, just to be more precise, this R5 with this strange signature. Okay. And now, well, as I said, that this is a kind of hyperboloid in which, well, x0 and x1 are playing the role of times. So and yeah, I said that well, in this that if you take these sets have the topology S1. Let me just bring this with me next to the picture to make it more clear. Okay, so this has topology S1, and then we have the other part, which is the R3 topology. So in this picture, this is represented as follows. So we have these circles, okay, such that R is constant. Well, in this representation, this R is corresponds to this to this relation, okay. So R is constant, and so they have the topology S1. So this circle, each of these circles correspond to sets defined by this relation, and then we have the T constant, which are lines of topology R. Okay, so this has the topology R. So if this was a is this is this this in this representation we are seeing a two-dimensional surface which has topology S1 cross R. But well, since this is a two-dimensional representation of a hypersurface in a space of 5 dimensions, we need to add 2 additional dimensions, and so we get the topology S1 cross R3, which I mentioned before. Okay. But the situation is similar to the situation I explained before with respect to the flat space-time and the cylinder. So I said that flat space-time could be defined on a plane and on a cylinder, and both are different manifolds because have different topologies, but the metric is the same. And so here something similar is happening. We have defined our metric, or 4-dimensional metric, in this surface, which is embedded in 5-dimensional space, in a 5-dimensional space. But it turns out that we can define also our metric on a 4-dimensional space, which has topology R4. And how do we go from this space to the space with topology R4? Well, it's the same as what we do to go from the cylinder to the plane. We take the cylinder and unwrap the cylinder and get a plane. So we take this sort of hyperboloid and wrap it and get something which is a kind of plane. Okay, and this something has the topology R4 and is where our metric is defined. And from now on, we will regard anti-de Sitter as a space, as a 4-dimensional space-time with topology R4. Okay. Yeah. Okay. Let me just write this down. So. Okay, So this is our chosen representation for anti-de Sitter, and we will work with this metric. Okay. Sorry, I just noticed there's a typo here because, well, this capital T is not capital T, is small t, where small t is related to capital T as by means of our rescaling. So one has to, well, in addition to these coordinate changes, one has to do a rescaling of t, of capital T. So one introduces small t by means of this relation. Okay, sorry about this mistake. Anyway, so this is our metric, and this is a metric in a space of topology R4. Okay, so this is all very beautiful, very nice, and yeah, well, you can check that this is indeed a space of constant sectional curvature. It's just a computation. Well, you can also do that with with the expression of the metric of de Sitter. I don't remember if I mentioned this previously, but the thing is that now that you have the metric, you can just take the metric and, well, compute Riemann tensor, compute Riese tensor, compute scalar curvature, and you get all the properties which a space of constant sectional curvature satisfies. In particular, you get that well, let me just see, I have here the relation. Yeah, so in particular, if you just do the computation, you obtain that there is a relation between this constant small a and the cosmological constant you have in the Einstein equations. So it's just computation which gives you this result. Okay, remember that in this case cosmological constant is negative, right? Okay, so that's what well, that's the geometric definition of anti-de Sitter. But what about its global structure? Well, to study its global structure, its global causal structure, well, we do the conformal compactification, and well, procedure is again the same as for the Minkowski and de Sitter. It's just doing some coordinate transformations until we find an expression of the metric which enables us to construct a conformal embedding. Okay, so, well, let me just describe the transformations. Well, let me just first take the expression of the metric for anti-de Sitter and bring it here. Okay, so that's what we have. And then, well, what we have to do is the following. Well, one can more or less guess what has to be done, but anyway, we shall do it. Okay, so this is the first transformation. Well, it's now just a computation, and you find the expression of the metric in the new coordinates. So now, well, we just do a rescaling of t. Okay, well, I am using again the, well, maybe, yeah, I have, well, let me just go back a second. And well, okay, we are now coming back to our original time, capital T. Okay, because we just want to pull this constant way, so that's why we introduced the rescaling, as you probably have already guessed. And so, well, we get, well, this is all very simple, and you already recognize the Einstein static universe. Okay, so this is now the metric of the So, okay, you may think that now things will proceed in a fashion similar to the previous cases. Well, there is some. It is not that's not quite true. We have to do something else, and you will understand why in a minute. Because okay, now we can. Once we have this, we can say okay. We can construct the conformal embedding of the zither into the Einstein static universe by the usual way. Okay, so we just identify this part with the pullback of the conformal embedding. Let me just write this here. Okay, so now where this G mu nu tilde is the metric of the Einstein static universe as usual. Okay, and now we can again just by doing that we have the chi function, which is of course the inverse, and so the zeros of the chi function enable us to obtain the conformal boundary. Well, here the zeros are clear. Okay, so well. Right, and well, we have to do the usual procedure of picking up a region which represents our original space-time, which in this case is anti-de Sitter, and that region, well, one of those possible regions is given by this condition. Okay, right. Well, I don't think I need to go into the full details because we have already studied the full details for Minkowski and de Sitter. But so this is and so let me just bring a picture of this conformal embedding. Okay, so here we have the picture. Again, have to rescale the picture to fit it into the screen. Okay, so this picture, you see the Einstein, the cylinder representing the Einstein static universe, and I have just highlighted the region which represents our physical space-time, which is anti-de Sitter, which is given by this condition. Because, well, you remember the circles, which represent S3 of the Einstein static universe. But the thing is that since we have this restriction, we only are allowed to pick half of the circle. Okay, because well, remember that the complete circle is given by this restriction. Okay, because this is the one of the polar angles of S3, but our physical spacetime is only this is only a subset defined by this relation. Okay, so this is just half of the S3, and that's what we have here. Okay, so cannot be perhaps seen well, but yeah, you see that this continues on the other side, and we have half of the S3. And yeah, indeed, well, we can already see the shape of the conformal boundary, which is when chi here is equal to pi half. Okay, so both of these points are points such that chi is equal to pi half, right? And in that case, well, if we add the missing dimensions, we easily realize that the topology of the conformal boundary is S2 cross R, okay, which is corresponds to this vertical line. In this vertical line, each point has the topology of S2, okay, right. But what happens here? What happens is that the region which we have here in the Einstein static universe is a region such that its closure is not compact, okay, because, well, this region corresponds as always to the image under the conformal embedding, okay, so it's this red region, but now we see in the picture that the cluster of that region is not a compact set, okay, so this is so okay, we have a conformal embedding as usual, but we don't have a conformal compactification. Can we do something about it? Well, yes, it's possible indeed to find a conformal compactification of anti-de Sitter, but as far as I know, not one cannot use for that Einstein static universe, because this, at least with these transformations, we didn't find a conformal compactification. Well, what we can do is, well, we can just go back to where to the expression of the metric we found, and we can just, well, do a further coordinate transformation which will enable us to find a conformal embedding of anti-de Sitter into another space-time. Okay, so let us just take this and do another transformation. Okay, sorry, I just didn't pick up all the metric, but anyway, we remember what is missing here. Okay, so just okay, so this is our expression of for the metric, and yeah, if we just take it and just introduce, well, because okay, the problem here is just the t is not well, it doesn't vary within the interior of a compact set, so we just have to introduce another time coordinate to solve that problem. Okay, it's not very difficult, as you can see. Okay, so now with this definition, we find that the new time tau is varying within the interior of a compact set. Okay, so now it's very simple to find the new expression of the metric. Okay, so yeah, well, I don't know what if I should. Okay, well, I just write the final result because the intermediate computations are all elementary. I don't want to bother you, to bore you anymore with elementary algebra. Okay. Okay, so this is what we have now, and now with the restrictions, this was the restriction we found above, and now this is the restriction for the tau for the new time. Okay, well, in any case, well, these restrictions come from the well, just to find by studying the zeros of the chi function, of this new chi function. Okay, so right. Okay. So okay. So these values correspond to the well, define the physical space-time, which is ADS4. Okay. Okay, but now, well, okay, we just look at the metric in within the round brackets. We see that this is not the Einstein static universe anymore, but we recognize a cosmological model. Okay, we recognize a closed cosmological model because we have here. Well, we have the metric of the round 3 sphere, and this corresponds to the scale factor, and this is the cosmological time. So yeah, this is one of the well, just can write the generic metric of this of the cosmological model. Okay, and this S3 is a 3 metric. In our case, this is just the 3 sphere, but well, you remember if you have followed a cosmology course, this could be a flat metric in 3 space, three-dimensional flat space. This could also be the hyperbolic space, three-dimensional hyperbolic space, so which corresponds to closed models, flat models, or open models. Okay, so in well, we can just give a picture of the cosmological model. All right. Well, here it is again. I have to again rescale picture. Okay. Right. A bit smaller. Okay, and so here in this picture we have that well, this corresponds to the Big Bang. This is the Big Crunch, and each of these red sets are the 3 spheres. Okay, so well, no, sorry, no, it's not. It's not that. It's the boundary of the red set. Well, it's not. This is not. I shouldn't have colored this in red. I should have colored in red only the boundary of this set, because I mean, our universe, the space, is not the interior of. It's just the the boundary. Okay, well, let me get. I mean, yeah, this has topology. Well, we have taken away in this picture 2 dimensions, so we have a kind of ellipsoid, but only it's just the surface of the ellipsoid which we are looking at here. Okay, and so when I said S3 is not the interior, it's just the boundary. This is just only the boundary. Okay, I should have taken that into account when I made the picture, but I hope that my explanations make the point clear. Okay, and so yeah, and so well, we have the chi-polar angle, which is parameterizing this circle. So each value of chi corresponds to 2 different points on this on the circle. Okay, right. And since so this is the description of the cosmological model, but we have done is that we have found a conformal embedding of anti-de Sitter into the cosmological model, right? So now this part of the metric represents the conformal embedding. And now G mu nu tilde is well, is this cosmological model, right? So in this case, well, yes, if I take the case of if I take the closed model, then now this corresponds to G mu nu tilde, right? Okay, and so now I just have to apply the restrictions which define ADS, these are the restrictions. So those restrictions imply that well, we just take chi equal to 0 as this point, and so chi increases. This point is chi equal to pi, right? And so we only have to consider the region in which chi goes from 0 to pi half. So this is chi equal to pi half, and the other side chi equal to pi half. And so it means that we just have half of this ellipsoid. We only need to consider half of the ellipsoid. Okay. One has to. I hope that you understand my drawing. I mean, I cannot draw. We really need to draw in 3 dimensions, but here I can only draw in 2 dimensions. So, but I hope that you understand that this is a 3-dimensional. Well, it's like a rugby ball, or and you are only considering half of its surface, right? Which is represented like this. And okay, so the boundary of the region is what I'm calling scry, which is now infinity, but now well, we only have well, we have to if we regard well, if we regard the points representing the Big Bang and the Big Crunch as separate, so it turns out that the scry has 2 components, which is one of the components is the component on one side of the rugby ball, and the other component is the component on the other side of the rugby ball, which we cannot see with this perspective. That we have to turn a bit the rugby ball to see the other component of scry. Well, it's possible to achieve a 2-dimensional representation of this, which is, well, let me just, we'll draw it next to I mean, if we will be able to peel off, well, take away the surface of the rugby ball which we are interested in, we could obtain something of this sort. Okay. Here we have two components of scribe, and then we have here these 2 points which in the cosmological model correspond to the Big Bang and the Big Crunch, but here will correspond to future time like infinity and past time like infinity. Okay, and so this region, the interior, well, let me just draw the lines better for reasons which will become clear later. Okay, well, maybe, sorry, I will just use the thinner pen. So the interior of this set corresponds to anti-de Sitter, right? So this is just as always the conformal embedding. Well, it's not with the sorry, let's just have to put it. Sorry about this. Right, but I think you understand what I mean. Okay, so yeah, and what are the properties now of this? How does this compare to the other cases which we already studied? Well, there are some properties which are easily visualized if we look at the diagram in the Einstein static universe, because here it might be a bit more difficult. Well, we just came here, we just obtained this because in this case, well, it's easy to see that for this conformal embedding, it's easy to see that, well, maybe I will, okay, I'm going to use a different name for the conformal embedding here, just not to confuse with the conformal embedding into the Einstein static universe. So it turns out that this now is a compact set. So this is this small phi. I just delete this, put this small phi. This small phi is truly defines a conformal compactification of anti-de Sitter. And this conformal compactification enables us to obtain these additional points, I plus and I minus, which we couldn't see in the diagram obtained from the conformal embedding in the Einstein universe, the Einstein static universe. Okay, we could only see the null infinity. So yeah, so well, and that's another additional reason why I am putting these 2 points in a separate fashion. Okay, and also we see that at these 2 points the conformal boundary is not smooth. We have well, because they correspond to the singularities of the cosmological model. Okay, but well, there's a thing which is easier to see in this picture, and is the null rays, because well, we know how null rays are in the Einstein universe. Okay, so yeah, we see here. Well, if we just draw this in a 2-dimensional picture, then we see the following. Okay, so maybe I can just put it here right below. Okay, so yeah, we have here the null rays, which are straight lines at 45 degrees. So as always, the knowledge of the null rays will enable us to draw causal curves. Well, this should be parallel, but okay, it's not easy to draw this, but I think you understand what I mean. Okay, and so yeah, the thing is that well, if we draw here a causal inextendable curve, well, we have to keep the slope of the curve between the two null rays, and well, we find curves of which never encounter the scribe boundary. The boundary defined with, well, I think I didn't set this during the lectures, but this letter is sometimes referred to as scry. Okay, so that's why I'm using this name scry, which is was the original. Well, I'm not sure how introduced this terminology. I don't know if this. I think it was Penrose's original terminology, but I'm not sure. But anyway, it has become standard terminology, and I am also using it. Okay, so coming back to the diagram, we see that there are curves which never meet the boundaries, and there are curves which start at the boundary and end at the boundary. Okay, so we have curves for, well, let me just put it in black. So for example, we can draw a curve which starts at the point of scry and ends at the point of scry. Okay, so well, maybe this is better seen the conformal compactification. This we can see clearly the different curves, because curves which don't meet the boundary defined by scry will meet the boundary defined at I plus and I minus. So this so what this also somehow justifies the terminology future time-like infinity and past time-like infinity, because there are time-like curves. Well, only time-like curves will end up in future in at these points, but in these points null curves could end up as well. Okay, well, maybe this is okay. Well, the null rays are examples. Null rays cannot reach the point. A null ray always have to start at the boundary at defined at one scry and end up at another scry, right? Another important property, which is easily seen in the representation in the Einstein universe, is that now scry are time-like hypersurfaces of the Einstein static universe. Okay. So this is different to what we saw in de Sitter and Minkowski. Remember that in de Sitter, scry was null, and in Minkowski, scry was null. In de Sitter, scry was space-like, and now here scry is time-like. Okay, and we saw that this difference in the causal character of scry brings differences in the global structure of each space-time. And yeah, here perhaps the main difference which time-like scry brings is that ATS4 is not globally hyperbolic. Okay, well, this, I mean, I am not going to give you a formal proof of that fact, But these representations, which we have obtained by means of the conformal embedding, allows us to guess that this is the case. Why? Because, well, I think this is perhaps it's easier to see this here, because we cannot find a hypersurface, a space-like hypersurface, which every causal inextendable curve has to meet. Okay, because, well, if you just keep drawing space-like hypersurfaces, you always see that there are inextendable causal curves which don't meet the hypersurface. It's somehow that, well, we can say that the existence of a time-like scribe enables information to come up to emerge from infinity constantly, because in the other cases new information couldn't come from infinity. Here the scribe, the time-like character of the scribe, implies that new information is coming up from infinity, and so we cannot put a space-like curve which somehow catches all the information which is coming from infinity. Okay, well, it is just a heuristic argument, but somehow it conveys the essential idea. Okay. So it, in that sense, anti-de Sitter is very different to the other two spacetimes, because the other two we saw that the other two spacetimes are globally hyperbolic. Okay. Okay. So. Yeah. So well, we have. I think that the study of conformal embeddings teaches us a great deal about the global properties of the simplest solutions of the Einstein equations. So it's important to know very well these diagrams. And in fact, well, in the case of anti-de Sitter, well, it's this time-like character of the well, the analysis of this conformal boundary has important implications in modern theoretical physics. Well, I'm not an expert in that field, so I cannot say much about it, but probably all of you have heard about the Maldacena conjecture and the ADS-CFT correspondence. Well, okay, so the core of these ideas is precisely this analysis of the conformal embedding of the anti-de Sitter into Einstein static universe, and the result that scribe is time-like. Okay, so this tells us that it's very important to know all these in detail. Okay, right. And to finish this study of the simplest solutions of the Einstein equations, well, I said that a lot of information can be obtained by just knowing the shape of the conformal diagram. So I'm just going, as a matter of summary, I'm just going to draw here the three diagrams of each of the spaces. Okay. So we have here. Sorry. Yes, this is just to summarize. Sorry. Well, okay. Let me just try to get. No. Okay, it's now a straight line. Okay, so just to remind you, this was Minkowski. Then we have the zither. And anti-de-Sitter. I'm just going to draw the conformal compactification. Okay. Well, in these lectures, we restricted our study to dimension 4, but, well, of course, these simple solutions can be defined in any dimension, and all these, well, these results about the conformal diagrams are generalized to any dimension. So I could have done the study in dimension n or dimension d, so, and then well, the results could have been the same. Okay, well, dimension, of course, d greater than 4. Okay, so in any in any of these dimensions, the results are the same. So we could have obtained these sort of diagrams, right? And well, you see that the shapes of the diagrams are different, and so that implies different properties, different global properties of the space-times, which we have already discussed. Okay, right. Okay, now in the next lectures, we're going to see what can be done for other solutions of the Einstein equations, which are not so simple. Okay, so stay tuned and see you in the next lecture.